Thank you for the introduction. I hope the voice is not too loud. Is it okay, or should it? It's okay. Okay, then let's. If it's too noisy, so I can speak softly, or I can move it around. So please let me know. So, well, first of all, I'd like to take this opportunity to thank the organizers for this beautiful workshop. I've been to China several times already, but this is my first time to this particular campus. I must say, I'm very impressed. And and today I'm going to talk about my series of works involving a collaboration with Wei Li, Professor Wei Li, who is at Beijing. So I benefited tremendously with a connection to also the Jakan Mao, who is currently a postdoc at ITVU here, writing a paper which we hope to publish soon. And I'm going to make this talk a little bit of concatenation of various different ingredients I have developed over the years. And the hope is that there are some people in the audience might not be string theorists, and hopefully there are some people from mathematics or computer science, and then at least portion of the talk should be very accessible. And so let's see. So let me begin by starting with an overview of what the question is and what type of things we want to discuss. So today I'm going to talk about Calabi-Yau geometry, as in the title. And of course, there are many talks about Calabi-Yaus, and it's a fascinating place where mathematics ideas and physics ideas interact with each other. And it's a fascinating topic. So I sometimes tempted to explain to a general public, and I still haven't come up with a good way to explain it. Quite often people try to use the projection like this. And sometimes I even download the data and ask somebody to 3D print it, and you get something like this. And whatever it is, at least it gives you a feeling. So obviously this is not complex three-dimensional, but at least the feeling is that, well, most of the parts, it's kind of smooth surface, of course, but sometimes there are singular parts. So that's the feeling of the Calabi-Yau. If you touch it, it feels like that. And this is the classical, what you might call classical Calabi-Yau, the usual Calabi-Yau. And it's a fascinating topic in itself, although what I'm going to discuss is, in a sense, the quantum mechanical version of the Calabi-Yau. So what is it? Well, first of all, the usual Calabi-Yau is a solution to Einstein equations. And in Einstein equations, you solve the classical equation of motion, Einstein equation. So, but now if you come to the theory of quantum gravity, the metric itself is supposed to fluctuate. And you never know what's going to happen. And I was looking around, and then this is one of the random pictures I found from NASA website. I don't need to see what it actually represents, but at least the idea is that the space-time itself fluctuates widely. And it might be that something pops up, and then that itself is a quantum mechanical process. And there are a lot of ideas. At least the Vita already said something like this, as far as I know. And there are many ideas like that. And so what exactly is a quantum geometry of this type? That's one of the questions which keeps me awake at night. I sometimes wonder, oh, what is the actual quantum Calabi-Yau? And of course, I don't know the answer, but it's a tempting question worth thinking about. What is the quantum geometry or the Calabi-Yau, whatever it is? And of course, we can talk about the philosophical implications, etc. But rather, we want to study it in a very concrete framework where things can be analyzed in a sophisticated mathematical framework. And of course, the string theory is a fascinating arena for such question, because string theory is, of course, the theory of quantum gravity. So we might hope to find answers, at least partial answers, even with the limited understanding of the string theory, what is quantum Calabi-Yau. And that is, of course, a well-defined question, although typically it's not the most straightforward question. Well, of course, partly because we don't know actually what string theory is, in a sense, but partly because there are competing effects. So in usual string theory, there is of course, the theory of strings. So there's a length scale associated with it, which is called the string length. And separated from that, there's a Planck length. And these are typically regarded to the same order, although there is a coupling constant actually in the power of the coupling constant separating between that. And in the typical situations involving weakly coupled string theory, the Planck scale is actually smaller. Planck scale is smaller, which means that if you try to probe things to smaller and smaller energies, what you encounter first is the string length. So I think that's why people begin to talk about stringy effects, stringy geometry, like the velocity instanton corrections and mirror symmetry. That is, of course, fascinating story. Of course, however, if you want to study the Planck length in itself, you have to first, in that situation, you first have to understand the stringy correction, and then only afterwards you can discuss the Planck corrections. So that's, in a sense, the embarrassment of riches of the string theory. String theory contains a lot of different things, and there is a Planck length, but it's kind of hidden in some layers of stringy correction. And now, if you want to try to go to directly explore quantum corrections, then there's a way to do that, which is to change the so-called string coupling constant, which I denote by GS. So when GS is small, as I said, that's typical situation of string theory. Planck length is much smaller. But as when the GS is large, and then Planck length is larger, you begin to see explore the quantum geometry directly rather than stringy geometry. Now, so in a sense, you need an interpolation between small coupling and large coupling. And I'm going to discuss this in the context of so-called topological string theory, where the coupling constant is topological string coupling constant. Now, in those situations, the two situations are maybe familiar to some of the mathematics-oriented audience. For example, well, this is the usual string perturbation theory, where you do an expansion with the genus, and in particular in terms of the coupling constant GS. Whereas there is a separate expansion, which is good when the GS is large. And GS is large, and in particular, this is a formal power series with respect to exponential minus GS. But sometimes people write as IGS, etc. But let's not worry about the factor. Don't worry too much about the factor of I. So here you have minus exponential GS. So this is an expansion where GS is large. When the GS is larger and larger, it's better. Mathematically, sometimes it's related to the Thomas invariance, so Thomas and these invariants. And so if you want to relate these two, you need a non-trivial interpolation. In fact, this is exponential, so you can just expand if you have infinite many terms contributing to the above. So, yes. Let's see. So it's going to be the BPS degeneracy I'm going to discuss, and in a sense, it's a resummation of this thing into this form. In my context, this is going to be the BPS degeneracy, and N plays a role of the charges of the difference. And exponential part is going to be the fugacities for that. I'll come to that. Yes, yeah. Well, let's see. Well, maybe I shouldn't, yeah. Maybe I shouldn't have said Gopakuma buffer. Gopakuma buffer is maybe, yeah. But at least this expansion certainly is an RG expansion, I think. Yes. Well, and in a sense, there's an interpretation between this and that is like GS plays a role of the inverse temperature. So it's like a start. So this part is more like a high temperature, and this type is a low temperature. So it's like you need a low temperature expansion, the high temperature expansion. So the point is that if you want to discuss quantum geometry, you need an expansion of this type, which is a little bit different from the typical expansions. Now, what I want to do is to discuss this in a very precise setup. And ideally, I can discuss that in a very general setup, like a compact Calabi-Yau, and the connection to black holes, and all that. Unfortunately, we are very far from analyzing that in practice. It's so difficult. So what I want to discuss is the classic setup studied by Okunfu, Rishik, and Baffa. I noticed that all speakers are in the conference, and Korea is even a local. So, and in this setup, the Calabi-Yau I'm going to consider just C3, first of all, just the Planck space. And in particular, it's non-compact. So the fact that it's non-compact means that the gravity decouples So you really cannot discuss some of the issues you might have in mind in the previous slides. But nevertheless, you can try to regard as a limit and extract some lessons out of it. And hopefully, the lesson is going to be applicable. At least some part of the lesson will be applicable to a more general situation involving compact Calabi-Yau, or more generally the question of quantum geometry. And yeah, whether that's really the case, we need only time will tell. That's what I'm going to do. And so, okay, so what these gentlemen do is they consider the so-called crystal melting model. And here, maybe it's a little bit difficult to see, but you have a corner. You have a corner, and oh, okay, so there is even a blackboard. So there is a corner, and then you're going to have some so-called 3D partitions, which is here, and that's the left-hand side figure. The right-hand side is the same figure, but looked from the opposite angle, from the other side of the slide. And so in this picture, there is a corner, and some boxes are taken from the corner one by one. And what they propose, so certainly this setup has been studied, in particular in connection with topological vertex, later generalized to an emulative invariance. But the particular aspect in its relation to quantum geometry is not as emphasized as much in my impression. So, and okay, so what we count is 3D partitions. If you know the definition, so you already know it. But if it's not, these are the example 3D partitions. But for example, this one is not. If you want to take this box, you need to take the one below. You can give a more formal definition. In fact, I'm going to give a more formal definition in much more general later. But hopefully the meaning is a little bit clear by just looking at the figures. So these are the concept of 3D partitions. And what was stated and also proved in the paper by Okunko, Yoshitake, and Baka is that you start with, first of all, topological A model partition function. So I'm not doing the full string theory, but the topological version of that, and on the non-compact C3. So that's a lot of simplifications, but let's start from there. And then that comes in written as the partition function, statistical mechanical model, crystal melting, which is the sum of the 3D partitions, also for the plane partitions. And then there's a weight, velocity Q, and lambda is the total number of boxes, where Q is exponential GX. And so this is their main result. In this particular case, there is a nice formula, infinite product form, and you can even expand, and that's their result. So that's proven. Now, you can ask the question of what is the meaning of this? Well, a priori, you might think that it might be just a coincidence. We are looking at trying to compute something, and it related to the sum of a crystal. But is there any meaning to this each individual term, for example? That's not a priori clear. It's just that it's written in some way, and whether there is a nice physics meaning to that directly, it's not that obvious. It's not that obvious. However, what was framed in the later paper of Kamran and also Nikita and also Iqbal is that these things should be regarded as some version of the quantum form. So so quantum form picture means that the geometry pops up one by one, and that's reminiscent of this picture where boxes, you're adding boxes one by one, or sometimes remove atoms, remove boxes. So that is their physics intuition, and they provide some argument for that. But for example, one of them is that you can go to the classical regime. So that's like going to the high temperature limit in the previous explanation. So we are starting with the low temperature expansion, so where you begin to remove boxes one by one, and that's a low temperature expansion. But then when you try to go to the high temperature expansion, you excite a lot of boxes. So much so that at some point it begins to look like a smooth surface. And you can show that that's a pure probability / mass problem. And then there is a nice shape which pops up here. That's an interesting topic in connection with the frame partition, but also diamond models in general. There are even talks related during the conference. And And then these shapes are called the limit shapes, limit shape, and it's given by a particular equation. And it turns out that this particular equation is a projection of the shape of the mirror Calabi-Yau three-fold. So I start with toric Calabi-Yau 3, take a mirror, which is still toric Calabi-Yau 3, and then project onto the kind of radial direction. It's called a neighbor projection. But whatever it is, so it's like a projection of the Calabi-Yau geometry. Now, there is a lot of questions like why mirror and things like that. Also, you don't necessarily see the full Calabi-Yau geometry, but somehow projections, etc. So I don't really claim to understand it well enough. But nevertheless, it's tempting that you're going to see the smooth geometry of the Calabi-Yau emerging in the thermodynamic limit. So what this means is that you can relate the low temperature expansion here to the high temperature expansion. And the quantum form picture here, which you have here, it seems to be consistent with the fact that classical geometry is present if you go to the high temperature regime. Well, of course, there is also a lot of interesting questions like what is the excitations around there, etc. And but that's I don't have too much to say about it. But at least the fact that classical geometry emerges is fascinating. Now, if you try to go backwards from this classical geometry, what this means is that this itself is a Calabi-Yau, classical Calabi-Yau. But now you have the quantum Calabi-Yau, and you start with the classical Calabi-Yau, go to the quantum Calabi-Yau. What looks like a smooth geometry is discretized into boxes. And so the boxes here, and in the rest of my talk, I'm going to refer to this, each box is an atom. And the reason is that if you want to consider more general configuration of the plane partitions, 3D partitions, in general, it consists of several different boxes. So I might call it like a molecule of these atoms. So what this picture says is that the classical Calabi-Yau geometry is very smooth. But when you go to the quantum regime, it's discretized into atoms. And then the actual atom, or actually molecules consisting of atoms. So they are only simple basic group. In this case, there's just one basic atom, and everything is made up from there. So that's a tentative picture of the quantum geometry. And so the question is that how to understand it. Well, you might object that this is a little bit too special. This is for C3, just the simplest Calabi-Yau ever you can think of. So you might be able to ask the question of how to generalize this to more general geometries. And unfortunately, for general Calabi-Yau, certainly for compact Calabi-Yau, I don't know the answer. But at first, we have a class of examples, in particular, infinite many examples for toric Calabi-Yau threefold. If you don't know what toric is, it's essentially like a Calabi-Yau threefold with a 3 torus vibrations. But the 3 torus might degenerate at some points, and how the degeneration happens is encoded in some combinatorial data. So you can start with the combinatorial data. Everything is combinatorial in principle, and then discuss everything. So that's why these examples are particularly tractable. Yes. Well, it doesn't have to be C3. Sorry, what's? Let's see, I'll find. Well, you can do, for example, conifold or generalized conifold, and yeah. Literally any toric Calabi-Yau 3, yes. Associated with the complex polygon. Yes, non-compact. Sorry, non-compact, yes. These are still non-compact, yes. So I have nothing to say about the compact case. I'm very interested. Well, of course, computing even the goal physics, but yeah, invariance for compact Calabi-Yau for physics, that's a long-standing problem. I think it's extremely important question, but I don't have anything to say. So, going to that direction is certainly one direction. What I'm doing here is that rather than going to that direction, at least for now, stay in the non-compact case, where some information might be lost, but we stay there. But in that situation, I go deeply into more algebraic structures, which comes up there. Okay, so what is the more general case? So the more general case is not too different. So it's a toric Calabi-Yau, but it's a Calabi-Yau 3-pore, and in particular non-compact. So what you might call the 6th cycle, the full Calabi-Yau is non-compact. However, it must still contain, for example, 2 cycles, 4 cycles, and in those cases, you can wrap the d-branes on that. So these are the number of charges, and in particular, they might be different 2 cycles. So it's a vector. So this is not just an integer, but multiple set of integers for each 2 cycle. And so that's like a specifying the number of d-branes. Or if you're a mathematician, you can say that it takes an element of the cohomology, the charge lattice. And then there is a fugacity, a formal power series for all of these invariants. So these are called BPS degeneracies in the physics language. If you're a mathematician, you might be tempted to call it the generalized Thomson-Thomas invariants. Well, it's generalized because in general it's a different chamber. So it's different from the original, what the original Thomson, in particular Thomas, defined. But it's a similar type of invariant defined from stability conditions. So this is the definition of the partition function. So it's a generating function of all the BPS degeneracies. Now, in this case, there is a statement which is very similar to what we had before. The statement is that it's the same as the crystal partition function. So that's the combinatorial result. So that's one of the main results we had. Well, if you're a physicist, you might be interested in the intermediate step. So these are the d-branes, like for example, d4 brane lapping 4 cycles. So there is one remaining direction. And we expect that to have a quantum mechanics, supersymmetric quantum mechanics in that direction. With the 4 supercharges. And then we want to have the Witten index. The BPS degeneracy I'm talking about can be regarded as a Witten index of quantum mechanics of that theory. And then you can use your favorite techniques. Originally, we used the argument using the equivalent localization. But after we wrote the paper, for example, people came up with the Jeffrey Carbon supersymmetric localization formula for the Witten index. So you can also use that to derive this. So there is a crystal partition function, and let's see. So now, what is the crystal partition function? So it's a little bit scary. In fact, whenever I give it to people, get discouraged by this picture. But sometimes people get either discouraged, or sometimes I get the feedback that this picture is so beautiful. but let's see. But the actual thing is not that complicated enough. I'm going to explain how this crystal is made in the later part. But let's say for me, for now, it's some combinatorial structure. And of course, what type of crystal you have depends on which toric Calabi-Yau you start with. And in this example, I start with toric Calabi-Yaus, where there are 2 compact P1s, which means that there are two type of integer fugacities you can turn on, in addition to the D0 brane fugacity. So it depends on 3 parameters. So the BPS partition function or the generating function of general PT imbalance depends on 3 parameters. It's a formal series of 3 parameters. And the formal 3 parameters are related to 3 parameters here. And then the number 3 is represented on the right-hand side by the fact that we have atoms of 3 different colors, black, white, and gray. Well, it's just a convention. And so this itself should be regarded as an analog of some three-dimensional crystals. And what you actually count when you want to, the crystal partition function itself is again defined by taking atoms from the top. So here there is a top. It's a little bit difficult to see. Maybe it's a bit difficult to see from back, but there is a 1 atom on the top of the crystal. If you stare at it a little bit, and then you start taking the atoms from there, 1 by 1. And then this is what you regard to be a molten configuration of molten crystal, which I might simply call the crystal from now on. And so this is a generalization of the 3D partition. The difference is that it depends on 3 parameters because atoms come in 3 different colors. And then when you compute the partition function, you just count the number of atoms in each crystal configurations. And that's the crystal partition function I define. So I invoke the Bragg magic, which is not the Bragg magic. but so far graph magic, which is how to construct a crystal. But at least the statement is that you can construct the crystal melting partition function, and then the story works in a similar way. And then why is this interesting? Because it means that the picture of the quantum form as consisting with small bits, which are called atoms, and atoms are combined together into molecules, and the large molecules give rise to classical geometry. That's at least not only for C3. It's for the statement is correct for infinite many examples for non-compact totally Calabi-Yau three-folds. Well, of course, the next question is then what is the implication for more general examples? And I'm slowly coming to that. But let's see. In the rest of my talk, I stay with this non-compact totally Calabi-Yau three. And then you can ask the question of what happens if you try to change the geometry yourself? Well, so sometimes you get the inspiration by talking with, I call them molecule, but the atomic physicists. So an atomic physicist, they can actually engineer things. Like they can bring two atoms together, optical trap, and bring them together to make a molecule, things like that. People can do amazing stuff. So then it's tempting to think like, what happens if I myself, at least in my mind, try to do similar manipulations. Namely, in this picture, I have a molecule consisting of some atoms. And then there is another atom, which I denote here, which you can bring from infinity far. And then slowly, gradually, adiabatically bring it together in such a way that you get a larger molecule with an extra atom. So you can imagine that there is a way to do such operation. So that's like a creation operator. You might call a creation operator. Or of course, you can do the other process too. You can take away one of the atoms from the molecule. So these are like annihilation operator. Well, in general, there are atoms of different types. For example, previously gray, white, black, etc. There are atoms of different colors. So when I do this operation, I can preferentially bring the atom with a specific color. So in general, there are different number of creation and annihilation operators, one for each type of atom. So that's a very intuitive picture. So really, like you might expect that this type of transition, so it's in a sense like a geometry changing transition in a widely fluctuating quantum form. And the effect of that is represented by this abstract sounding operator E and F. That's the mental picture I have in mind. And then the question is that, okay, so what are the properties satisfied by these operations? And I'm going to, let's see, in the end, give you the answer somewhat top down. If you're interested in justifying that more down to earth, I had a paper with Dima Garakov, which try to explain to some extent. But let me just have one slide why you might expect a non-trivial algebra. So here I have a simple picture where I bring in one atom of one type and another atom of different type, type A and type B. So it's like to bring in two things together. And then you can ask the question of what happens if you try to do this in opposite order? Particle one, bring in A and B or B and A. Clearly, the final result is the same because you brought both A and B together. But it turns out that actually these two are not exactly the same. And there is some factor coming out. Well, if you're mathematicians, this is essentially what the shuffle algebra does. Why it gives us the shuffle algebra requires a little bit more explanation, but it's a shuffle algebra if you like. But if you have, here I give a more physical explanation, which is that these are the particles with the electric magnetic charging. So these are like a dionic particles. And in particular, when you bring in the two dionic particles, they are mutually non-local. In other words, there's like an angular momentum in between. And in those situations, you end up in the same thing, but there's a non-trivial phase factor, like a magnetic version of the Harlan-Coleman effect. So this shows that you might expect a non-trivial algebra, partly because of electromagnetic pairing. And And it turns out electromagnetic pairing in the case I'm going to talk about is determined by the date of the quiver. Electromagnetic pairing of the electromagnetic particles are determined by the quiver. So it turns out that the quiver is going to be the data specifying this algebra. So that's at least a mental picture of why you might expect a non-trivial algebra. So this is the result. And then in the rest of my talk, I'm going to explain what the end result is. So, okay, so there was I just explained that you might have said non-trivial algebra. And what is it? Well, because it's abstractly defined by bringing the particles together, etc. So you might argue that it's like if you use the physics intuition, it's implicitly well defined. But I want to do something concrete. And for that, I need the explicit generators and relations so that you can write down everything explicitly in such a way that you don't need to know where it comes from. You can just look at the algebra and then study it. And it turns out that such answer is provided by the Quiver-Yangian, which I'm going to define in the rest of my talk. And there is a non-trivial statement that the BPS partition function, which was written as a combinatoric crystal melting model, is the same as the character of the Quiver-Yangian with respect to a particular representation. So if you like, this is a version of the geometric representation theory. So there's algebra acting on the geometry, and then there's and then the one inclination of that is the character, and the character is the BPS partition function. And that's consistent with the fact that the algebra is the creation annihilation operator of the quantum Calabi-Yau. Okay, so that's the main part. And let's see. So since I have a little bit more time, so I can try to explain. So far, I didn't explain some of the details. So I can try to be not all the details, but at least a little bit more concretely as to what the ingredients are. And for that, I need to start with the crystal itself. And one of the ideas is to instead of starting with the toric Calabi-Yau suite, so this is a geometry. But in the following, I'm not really going to talk too much about the Calabi-Yau geometry itself, but rather discuss the quiver. Quiver is just the oriented graph together with the superpotential, and you're going to see some example of that. And well, if you're a physicist, you can regard as the defining data of the whole supersymmetric quiver quantum mechanics, where arrows are bifundamentals and vertices are gauge groups. And so the quiver is always the starting point. Well, fortunately, there's a dictionary going between toric Calabi-Yau fields, quantum mechanics, this data. Well, that goes back to Douglas Muller. But for more general toric Calabi-Yau, there are a series of papers on so-called brain times by Hanani and others, many other people. So working this out. So I'm going to take that advantage of that. And so I'm going to, my starting point was a quiver with superpotential. So it's very algebraic. And so it's somewhat similar to the spirit of the algebraic geometry, where instead of starting with geometry, I have the underlying algebra. I'm going to define some algebra. Although the algebra itself is not a commutative algebra, I'm going to define algebra, which is not a commutative algebra in general, and then do some manipulations of that. And the hope is that such algebraic structures are better for the purposes of what happens to the quantum Calabi-Yau, because when it becomes a quantum Calabi-Yau, the geometry is not too clear. So maybe the algebra might play better roles. And once you start with this quiver with potential, superpotential, then I'm going to define the crystal melting and then Quiver-Yangian. And it turns out that, and then there's a non-trivial statement that Quiver-Yangian acts on the crystal melting as a representation in such a way that the weight space of the representation is the crystal melting. In the particular melting configuration of the crystal, what I call like a generalization of 3D partitions. So that's the story I'm going to explain. And what I'm going to do is first explain the crystal melting part, and then define the Quiver-Yangian. And I don't know how much of time, but I try to explain how it acts on that. So there are three parts, each of the ingredients, and then the relation between the two. And in fact, so I'm going to discuss the general toric Calabi-Yau 3, which is combinatorially complicated. But one of the insights I had back then in the 2008 or so is that actually if you study the example C3, the simplest example, all the ingredients are there. You just need to adapt it to, in fact, all the words you can straightforwardly copy to modular Calabi-Yau, but you have to see the structure. So because of that, I'm coming back to the example C3. So C3 is described by this figure. It's just a single node with the 3 arrows. And then there is a superpotential, which is trace x by z minus x z y. So trace means that it's a cyclic invariant. And the meaning of the trace is that you consider the derivative, ideal generated by derivative, the so-called Jacobian ideal. And in this case, it means that the x, y, y, z, z, x, they just all commute. So if you consider the algebra of all these operators, modulo this relation, so it's like a chiral ring. And then you just have a polynomial in x, y, z because they commute. And of course, this is a natural because it's a spec of C3. But the important point is that consider this algebra, which I call the path algebra. So for each arrow, there's element. You can naturally define a concatenation by concatenation path, modeled out by the Jacobian ideal. And once you have this, it's easy to see the crystal structure because this is the path algebra. And if you look at the element of the path algebra, it's a polynomial x, y, z. In particular, it's the form x to the I, y to j, z to k, labeled by 3 sets of integers, non-negative integers, and then three sets of integers correspond to position I, j, k in the folder octant. And so the atom, whatever referring to atom, in this case, the box of the 3D partition is just element of this path algebra. And okay, well, first this is just one atom, and for discussing the 3D partition, you need to have a collection of atoms satisfying certain conditions. And well, there are different ways of saying that. For example, typical definition of 3D partition is that you cut the 3D partition to 2D pieces and impose the condition, interlacing condition, etc. Although there is a little bit different way of saying that. So if you regard the set of lambda, it's a finite set. It's a collection of points or collection of monomials. And you can consider the complement of that. And that is like the ideal of the path algebra, which is the polynomial ring. And so ideal means that if you take a boxes, for example, if you take a boxes somewhere here, and then multiply by x, y, z, like increasing in x, y, z direction by coordinate 1, it's still in the complement. You don't come back to the inside of the sum. Maybe I explained it fast, but it's a simple way to see that this is exactly the one way to characterize the 3D partition. So maybe you have the path algebra and then consider ideal whose complement is finite dimension. So that is a characterization of 3D partitions. Yeah. So, but now the good thing is that once you reformulate it that way, you can literally copy everything. This is a more complicated example, in a sense, a little scary example with a 3-node quiver. With many arrows. Well, it's like a super Deakin diagram. So there is a bosonic node here with this vertex or adjoint, and there is no adjoint here. So it's some quiver. You know what the corresponding geometry is? Geometry is the form xy equals zw squared. So anyway, you start with the quiver, and it turns out that the superpotential is also known. Yeah, so to explain that requires a little bit of time, but at least the point is that if you start with this data, quiver with relations, and then you can get the path algebra for this quiver. Again, by considering the set of paths, modulo the relations. Well, in this case, there are multiple nodes. So sometimes you cannot concatenate the paths because they start and end at different points. In that case, you define the product to be 0. And of course, in the path algebra, each of the paths might start at vertex 1, 2, 3. But let's say fix the vertex 1, and then consider the set of paths starting with vertex 1. Modulo the relations coming from this superpotential. That's known as the path algebra. So yeah, and then just like before, if you take an element of this path algebra, you say that it's atom of the crystal. That's more or less how I constructed the previous picture. Yeah, let me try to be a little bit more explicit. For example, here I declare that I want to start with vertex 1. And then let's see, for example, this is one example of such a path. Like I start with 1, going along 1 twice, and then go back to 3 next, go to 2 and come back. So that's an example of element of the pulse algebra. So I declare that there is atom associated with that. Now, there is also another atom associated with this picture. It's almost the same picture, but you don't take the last step. So far, the atom is just abstractly defined as a set. But there's a very natural way to connect these sets. Because, for example, if you look at these two, these are related by adding one extra arrow. So in this case, I draw an arrow like this. And you can see that there is it makes a kind of like a structure, a graph, vertices of atoms, and then there is also connectivity defined by arrows. So which looks reasonably close to crystals. So here it just like looks like a tree, but in general it's not really like a tree. Sometimes it branches off and then come back to the same point. It needs to be identified, and that's because you need to divide by the Jacobian ideals. So one of the relations of the Jacobian ideals says that this path, starting 1 to 3 and come back, is actually the same as going to another vertex 2 and come back, for example. So these two are different paths, clearly, if you just look at it. But if you take the relations into account, they are identified. So it's not exactly like a tree. Sometimes it comes back to the same point. And so that's how you get the graph. And that's more or less how you define the crystal. However, there is a little bit more data. If you want to place the atom in a specific position in the 3 dimensions, you need a coordinate. What is the coordinate for that? Well, the idea is that you're going to associate the charges to that path. So each of the atoms is just a collection of paths. Here, for example, it's an example, red path, like in this case, coordination of 4 edge arrows. And each arrow is like a bifundamental. And then you can assign a charge, the Freiberg charge, to that arrow, and each of that is sum it up, and then you get the Freiberg charge. So you simply, or if you don't like a word Freiberg charge, you can say that there is an equivalent torus action. There is a toric action, and which descends the action on this arrows, and these are the parameters. But either way, you can associate naturally a set of parameters to each of the arrows, and use that to put the atoms in specific directions. And it's a toric Calabi-Yau 3, so there are 3 different directions, except that there is one particular direction which physically corresponds to R charge. So you typically regard it as one special direction. So that's how you get the 3 dimensions. And sometimes quite often people project onto the R symmetry directions, and you get the picture down here. And that was the projection I was denoting before. Okay, so this is the thing, and then once you have that, that's how I explained how to get this. But once you get this, you don't have to worry too much about how to get it. Well, you can just for fun, you can just keep going around. It's a little bit difficult to see, but there is a red arrow you're not supposed to take, and green arrow you can take. But for example, the simplest path is you can just start from this crystal atom and then keep going down the crystal. And then that's like keep starting with vertex 1 and keep going around. So for each path, you can associate for each. If you keep taking atoms from the top, there is a corresponding path like this. But each path corresponds to a particular atom here. So in a sense, if you want to, so for example, if there's an atom here, in general, let's see, in this case, a little bit there's just one way, but in general, if you take so this is starting point. In general, they want to come alive here. And then there are multiple different paths in general, and multiple different paths, but this crystal is structured in such a way that actually F-term equivalent. So they are regarded as the same element. And then, so it looks like there are 2 different representations, but they are the same. So the short answer is that so each atom here is the particular path, starting from the vertex here, modulo the F-term relation. Okay, so this is the combinatoric part, and but the main message is that, well, first of all, it's defined through the quiver with the potential, and then once you have that, the rule is almost the same as C3, but you need to interpret the slightly more general way. And of course, the reason I talk about this is that this is defined somewhat very, very combinatorially. So you might ask, like, oh, what is the physics meaning of this? But of course, the hope is that this purely combinatorial looking structure, it might tell you something about the quantum aspects of toric Calabi-Yau 3. Now, so this is one side of the story. And another side of the story is to define the algebra. So this is like a geometry itself, but now you want to construct the quantum Calabi-Yau by bringing atoms together or removing atoms, and then see what type of structure there is. And then that's known as the Kuiper-Yangian. So it's again determined by the Kuiper with the potential, the same data as before. Well, I call it the Yangian because it contains as a special case, so-called affine Yangian, the Yangian associated with the affine type Dickey diagram. So it's an extension of the standard Yangian, which covers the integrable models. But this one is much more general. Okay, so let's see. So and then what is the algebra? Well, one of the simplest ways is to just define it using generators in relation. Yeah, as I said, I really wanted to have something concrete because sometimes in mathematical literature there are very general definitions, but sometimes I have trouble seeing how to compute it, etc. This one is very concrete in that sense. So you have an infinite collection of generators. For EA, for example, A is a vertex of the Kuiper. So in the previous example, like a 3 vertices, so there are 3 copies. And that's what you would expect because there are different types of creation annihilation operator for these atoms. And then so creation operator, annihilation operator, there is also like something like a Cartan, which I do not psi. And each of these depend on spectral parameters. So they actually, if you expand, it looks like infinitely many generators. So somewhat similar to fields in the conformal field theory or vertex operator algebras, which is not a coincidence. In some cases, you can, the Kuiper-Yangian is indeed related to W algebra in some cases. But in any case, so far at this point, it's just a useful way of repackaging the generators. And on each vertex, there is a Z2 gradient, whether it's a boson or fermion. And the rule is that whenever there is an arrow coming back to the same node, you declare it to be a boson. The intuition is whenever there's an arrow come back to itself, you can keep going around. And it sounds like a boson where you can create many bosons. Okay, but anyway, this is the definition if you like. And then the relations are given by this relation. So here, well, first of all, this delta is just a z minus w. So for example, if you look at this first one, psi create at z and w, and but they commute. But sometimes there's an interesting factor. Okay, there's a Z2 grading. So because of that, there's a plus minus sign. It makes things complicated. And then there's a meaning like this sim equal. And that means the equality up to some terms. So it means the equality of the singular terms. But let's see. And then there is a, maybe, for example, if you look at this relation between E relation, E relation, then there is a non-trivial factor here, which is a rational function. And for each pair of A and B. So remember that A and B's are like a creation operator for each vertex. So it creates an atom of particular type. And in general, if they are not connected, the corresponding vertex is not connected by Kuiper, they're mutually local. So they actually commute. But if they are not disconnected in the Kuiper, they are connected by the Kuiper, and then you have to take into account something like a Harmonic phase. And the role is played by this expression, where it's a rational function. So with the degree, it's given by the number of arrows from E to A or A to B. So you can try to just justify this from computation, one loop determinant of wave function, etc. But here I'm just giving it as an answer. So there is some factor which comes up. And the same factor appears here and there multiple times. And then finally, there is this relation. So this is like a super commutator. The super commutator EF is related to psi. So things are a little bit scary to some extent, but if you stare it a little bit, certainly many of the structures. For example, there is a involution extending E and F and side to side inverse or something. So you can remove approximately half of them, and then the structure is essentially determined by the single function. Now you can ask, let's see, what happened to the superpotential? If I declare that everything depends on superpotential, well, actually, I haven't used the superpotential that much, except to say that the parameter which appears here are constrained. So this is the product of an edge. And for each edge, I'm going to associate some charge of that associated by fundamental. And that has to be compatible with the superpotential. So these are like the parameters. These are the same parameters which I used when I press the crystal into the precise three-dimensional configuration. And so the superpotential appears only illusory, which is actually typical in supersymmetric localization. Okay, so these are the definition of the quiver, generators and relations. So now something is concrete, so I really try to encourage all the mathematicians to look at it. There are some papers by André Negou, for example, related with that, but very few so far. And in some special cases, okay, maybe I listed too much, but in some special cases, it's corresponds to affine Youngian GL_M. This is probably the most general case. Affine Youngian GL_M. So it's some known algebra studied previously by Mukin et al. And however, in the general case, if you start with a general quiver, if you start with a general toric Calabi-Yau, you get a general quiver, and it seems that this algebra has not been studied. Well, in fact, there are many affine Youngians or Youngians or variation of Youngians, but quite often they start with the Lie algebra and then try to deform it one by one and things like that. So there is always depends on G. But here in this case, the starting point is not the Lie algebra. The starting point is the quiver. So you have a natural set of algebras starting with the quiver, which, in my opinion, is of some interesting mathematical interest. Okay, so now I have like 8 minutes or so. So I can try to explain a little bit how to connect the two stories. So far, I explained the crystal melting, like a quantum form of the toric Calabi 3. And then I have somewhat top-down define the quiver Youngian. Now you can ask the question, how are these two related? And of course, the short answer is that quiver Youngian acts on the crystal. In fact, historically, that's actually how we found it. So what it should do is clear, because I already gave you an introduction of what we would expect. So first of all, there is E generator. And these are supposed to be creation operators of the quantum form. So what means is that if you start with the K, for example, okay, it's a little bit simplistic picture, but if this is K, and then you should add one more box. That's like an EA of type A. And of course, there is not a unique way. In this case, for example, you can add it here multiple different ways. So you need to sum up all the possible ways of adding extra atom to the molecule. But it's a three-dimensional partition. Actually, you can start with here, but I don't list everything. And then F is the same. F is just a removing operation. And psi is a diagonal, so it acts as it doesn't do anything up to it just acts as a multiplicative operator. And now the interesting thing is that when you create the atom, there is a pole. You are going to create a pole with this parameter Z. So it's a formal parameter. People call it a spectral parameter, and you're going to create a pole to the position of this atom A. So this atom itself is a collection of atoms, so it's located at a particular point in the crystal. So there are some numbers, and then that appears here. So it represents the fact that there is a pole, means that something is located there. So you're going to create the atom there, and then thereby creating a pole. And then let's see. And then of course, the subtle part is to determine this coefficient, precise numerical coefficient. And it turns out that precise numerical coefficient you can actually determine by imposing the condition that this gives a representation of the quiver Youngian. And it turns out that the details doesn't matter, but these are the residues of some function, which is almost like a product of this size. So size are the electromagnetic factors. Maybe I should go back. There is this braiding factor, which I call the factor by phi, appearing in this thing. And if you take a product of these things, you get to some rational function and take some residue. That's how you get a representation. So it's a little bit more complicated than the usual algebra, like SL2, representation SL2, because there's a spectral parameter and there's a pole, and also the combinatorial structure is 3D crystal, not like the simple highest weight state, but it's actually very similar. It's very similar to typical Gamma module type construction. Now, well, of course, it's supposed to be that, I didn't specify, but it's supposed to be representing a particular representation. So there should be some counterpart of the highest weight, somewhere here. And it turns out that's hidden in this small size zero. So, so that's the factor, which is which determines how the psi generator, Cartan generator, acts on the empty crystal. So it's like so this is like a highest weight, and so just empty crystal, and then let the Cartans act, and there is some rational function coming up. And then this thing determines the partition function. Sorry, the representation of the Euler-Yangian. And in the standard case, I'm going to take 1 over z. And if you have 1 over z, it means that you're going to create a pole at z equal to 0, which means that you're going to start place an atom here, so that you start growing the crystal from z equal to 0. And then there is like a tower of states. But you can do more general stuff. For example, there can be null states. For example, in this picture, you start growing from there. And at some point, it stops growing at this particular position, z equal to z. In this case, zd. And that happens when there's a canceling 0 in this expression. You can also try to do this type of crystal. In general, you start growing, and there's going to be duplications. But you're going to, you can delete the duplications by having a pole, having a 0, having 2 poles to start growing the crystal twice. But then when there is overlap, you have the 0 to cancel it, such that you have exactly this figure. So it's certainly, this is very similar to Dreamfield polynomial in the Yangian, in my opinion. But so the point is that you can construct a very general class of representations starting with this. So sometimes people worry that, okay, I defined the algebra top down, so is it a consistent algebra? So, but at least you can show that there exist non-trivial representations. Now, before finishing, I have one comment, which is that, okay, so here you start with the crystal, etc., which corresponds to a particular representation. But now you say that there are many representations. So you can ask the question, what is the geometrical meaning of these different representations? And it turns out that different representations correspond to the different BPS state counting correspond to different chambers of the Kähler module. So that aspect I didn't emphasize here, but in general, there's something known as a log crossing phenomenon, and the BPS state counting jumps along complex 4-dimensional locus. So there are actually many different countings. And then these different countings are reproduced by different shape of the crystal. And these different shapes of the crystal correspond to different representations. So in this case, I don't know how general the phenomenon is. In this case, there is a single algebra, at least for purpose. And then you can consider different representations, represent different BPS GRCs. So, okay, so I guess the time is up. So let me try to summarize. So technically, what I described is the follows. So I start with the toric characteristic. Again, I emphasize that it's non-compact with a difference that in holomorphic cycles, and there is a BPS partition function. So if you like, these are the non-compact analog of the black hole partition function. And then you can first relate to the crystal partition function, which you can construct from the data of the Weber quantum mechanics. And then the physical meaning of that is that that's like a quantum form. Now, you can go even further. The recent story is that you can go even further and consider infinite dimensional algebra, which are even new algebras. And if you consider the representations, then you have the character, and the character is the same as all these partition functions defined previously. Now, there are many questions. Well, for example, you can discuss what happens in a more general case. yeah, I have a forthcoming paper on that. So those are restricted typically to non-compact setup. But certainly the most interesting question is what happens if you try to go to compact cases. In that case, it's not even clear whether there is a general equivalent description and all that. But hopefully what we learned here, that there is algebra or the quantum form has wider implications. And so that's a physics context, but of course, mathematically, it's related to the so-called double of the cohomological Hall algebra. So this is the double of the cohomological Hall algebra. And while there are a lot of discussions, but not too much with the general superpotentials as I'm discussing here. So there are a lot of opportunities for further interaction between mathematics and physics. And of course, the final point I want to emphasize again is that whether we can extract more general lessons about quantum geometries from this type of analysis. Thank you.
You start with favor with the super.
Yes.
Can you do the same for favor?
Well, let's see. Yeah, I mean, that's true. So it's not, let's see. For some aspect, let's see. Yeah, for many aspects, you mean the relations which don't come from superpotentials. Yeah, let's see. Yeah, it's a, let's see. I think it works because as long as the charges are consistent with the relations, yes, I think it works. Although I might need to worry a little bit about some details of the representation, but I suspect it works. Yeah, right. So for certainly you can adapt the definition of Quiver-Yangian. For example, you use only the relations and the charges compatible with that. So there is certainly a Quiver-Yangian. Of course, more non-trivial question is whether that whatever defined abstractly acts on the crystal as well. And I suspect that works here as well. But I need to check some of the details. Yeah, you have to be reasonably careful. Yeah, in this situation. For example, I mean, you might be tempted to think that, okay, this works general, so why don't you consider more completely general Quiver with completely general superpotential? So, that's tempting, but I don't think it works in general. For example, the trivial example is that you choose a superpotential in such a way that supersymmetry is broken, for example. So there is no BPS step counting. So algebra acts trivially, etc. So you have to be a little bit careful as to what Quivers and superpotential talk about, or relations we talk about. Any other questions?
So you for the quiver, consider both finite size and also to take a larger limit.
Sorry, yes.
So the quiver, the size finite.
Okay, quiver, the size of the quiver. Well, let's see. Quiver, you mean the length of the quiver or the size of the quiver itself? You mean too many nodes, for example? Yeah, so you can interpret. So if you're talking about the large number of nodes, for example, you can talk about AN type, for example, and then take the limit where n goes to infinity. And yeah, it's like an infinite orbital. And yeah, I think that's an interesting question. I mean, for example, geometrically, you expect that because like a seat, for example, this one simply says C2 over Zn, and then take n to infinity. And then Zn goes to U1, for example. So yeah, essentially dimension reduces to lower dimensional theory. There are some situations like that. Although, so yeah, there could be some interesting answer. From this picture itself, it seems not too trivial to discuss it because it's like a number of different colors of the atoms. So you have infinitely many colors, for example. So you have to do the combinatorial accounting there. You literally adopt it. So that's one way. But of course, you can do other type of large n. For example, you can discuss the length of the group, for example. So here you have a quiver and you have associated un, and then take n to large. That's the standard holographic dictionary. And then you can try to do much with them. Yeah, a lot of discussions of holography. Yes, that's another direction.
I have was about so as you know, there's other generalizations we could talk about, like Z top and Z top bar, and, for example, gauge theory, and like this explaining the local curve or something like this.
Okay.
How does the does the atomic picture generalize in that case?
Well, you mean Z top bar? The crystal picture is precisely the chamber where there is a non-commutative DT invariant. Yes. So at least in the class of geometry, we started with Kamran, Hiroshi, and Nina, like with a compact cosine, like a strip geometries. In those cases, the canonical chamber we discuss here in this picture corresponds to Z top bar. And if you do the wall crossing, you're going to strip away the factor one by one, all the way. And then if you go all the way, you can get usual Z top, where there's a DT connection. So that was in fact discussed by Nagao Nakajima in the
What about the
context.
quiver picture? Is that also?
Yeah, in the Quiver-Yangian picture, it corresponds to changing the representation one by one. So different shape of the crystal. So it's like a changing the shape of the crystal. And or if you go back to the quiver, it's like starting with the one thing which I didn't emphasize actually is that you need to talk about the framed quiver, not just the quiver itself. And then if you have a framed quiver, you need to associate some arrows in between. You know, in general, superpotential is compatible with that. And there are infinite choices, different choices of, for example, in the quantiform case, there are two nodes, one framed arrow. And then there are number of arrows n and n minus one, n incoming and n minus one outgoing. Yeah. So, and then that n is an integer, which specifies the different chambers. And when n is zero or so, that's the z top bar. But when n is infinity, that's the limit where you get just z top. So the framing, the change of the framing is the data which is seen there in the Quiver language.